In this video, we'll be discussing cylindrical and spherical coordinates. So, cylindrical coordinates involve the quantities r, theta, and z. So r and theta are similar to polar coordinates in 2D, and we just end up tacking on an extra coordinate z, which stands for the height, right? The z height, as you can see in the picture. You can also tell that the formulas are similar to in polar. You have the same transformations going on with x and y, and with r and theta. And z is actually just the same, going from Cartesian to cylindrical. Right. So it is pretty understandable how these formulas arise. Perhaps just in case you don't know that, we can mention it. So just thinking about how this works in polar, you have this kind of triangle, and this would be the point x comma y, and then thinking about what is the length of the hypotenuse of this right triangle, you would end up using Pythagorean theorem, so you'd get that x squared plus y squared, x squared plus y squared is equal to r squared. And then by considering this angle and setting up, maybe I'll also label the sides of the triangle, setting up a trig expression that relates the sides of the triangle. Well, the easiest thing is to relate the sides that you are immediately given, which are x and y. And so the trig function that relates the two is tangent, and it's going to be opposite over adjacent, y over x. So that's how we wind up with these two equations. And then for the other two, converting from polar back to Cartesian, well, the easiest way the way I usually think about this is I relate it to the a triangle that lives on the unit circle. So a triangle living on the unit circle has the hypotenuse equaling 1, and then one thing that you know is that the point xy is actually cosine theta. Can I move this? Let me see. There should be a selection tool. Okay. So, yeah, the point, if you read it in Cartesian, it can be expressed as cosine theta sine theta. The length of this side is cosine theta, the length of this side is sine theta. And that's related to how the trig ratios are set up. You have that cosine theta is defined to be the opposite over the hypotenuse. Well, when the hypotenuse is 1, you're getting that sine of theta is this side divided by 1, hence this side is equal to sine theta. And similarly, cosine is defined to be adjacent over hypotenuse. When hypotenuse is 1, that means that the adjacent side is equal to cosine of theta. Then by scaling this triangle up by multiplying all the sides by r, you can get sufficiently far away and end up with these equations here. So that explains how we know that these formulas are true. You don't necessarily need to know the explanation. In the work, it's effectively just plugging things into these conversion formulas to allow you to convert from one coordinate system to another. I'm going to immediately lead into spherical coordinates. So this is yet another way of describing coordinates in 3 dimensions. So instead of r, theta, and z, we have 3 angles, or no, 2 angles and one length, basically. So rho it stands for radius. So rho is like the Greek version of the letter R. So you can think of it as being synonymous with radius. So that's the distance from the point in question to the origin. And then you have these two angles, theta and phi. Theta is the same as in polar. So if you take your point and you project it down to the xy plane, the way you describe the theta is still based around the two-dimensional polar convention. So I should maybe make sure that it's clear that along this x-axis, we actually have that theta is equal to 0, right? Because that lines up with, in this picture, we have x and y, our two-dimensional coordinate system, right? Along the x-axis, theta is 0. So theta, the x-axis is pointing towards us instead of to the right, but that's like we've rotated our space a little bit just to make things look in this way, right? And along the y-axis, theta would be pi over 2. So that explains theta, and the convention should be to have your angle theta be within 0 to 2 pi. There are some instances where it can make sense to make it be between, say, minus pi and pi. Either convention is okay. We would like to think that the radius should be positive. There might be some instances where it makes sense to make the radius be negative, but you can always re-express if rho is negative, you can always re-express that in a different way, so that it's based on just changing these angles. Okay, let's talk about the third angle. So the third angle is this angle phi, which you might also write like that. I, for some reason, chose to use this straighter version of phi here. So this is the angle of declination from the positive z-axis. So if your point were along the positive z-axis here, phi would be equal to 0. And then as you decrease your angle, which is what we call the angle of declination, you see that phi is drawn like this. So how much we angle ourselves away from the positive z-axis, that measures phi. And you can see that the furthest we can go is if we are on the negative z-axis. If we're on the negative z-axis, our angle phi is actually going to be pi. If we go further than that, we could actually swing our theta around to the other side, which would make the phi into something within 0 to 2 pi, or 0 to pi. So you can always express every point in three-dimensional space you can express so that rho is greater than or equal to 0, phi is between 0 and 2 pi, or theta, sorry, is between 0 and 2 pi, and phi is between 0 and pi. That labeling is always possible, and that is the typical convention to do that. Okay. And we have, well, more conversion formulas. So converting between spherical and rectangular, you can see that there's two trig functions. So these are gonna be things you get used to. They can be a little bothersome to work with, especially when we eventually talk about the Jacobian. Yeah. And the formula is going the other way around. So you can see that this one is the Pythagorean theorem, right? Rho squared is equal to x squared plus y squared plus z squared. This one is the same as in the polar case, so you can see that it's completely the same formula. And this is a little bit messy, but it's, you can just plug right in. You can actually think about why these formulas hold. You can reason about it geometrically, but I don't think it's necessary to mention that. So I'm going to skip over that. And then, well, I wrote this here for completeness, so the book does give you these as well, formulas to convert directly between cylindrical and spherical. Though, you could just as easily convert from, say, spherical to rectangular and then rectangular to cylindrical. So there is a way to work around having these formulas. Some people don't teach these because you can just sort of proxy things through the rectangular coordinate system to convert between spherical and cylindrical. Okay. Now let's see some example problems. Right. So suppose you're given this point in cylindrical coordinates. Then the problem wants you to find the representation in terms of the rectangular coordinate system. So you just plug into the conversion formulas. So given r, theta, and z, x is up here. It is r. We use r cosine theta, r sine theta, and z stays as z. So that is what I do. R cosine theta, r sine theta, and then you just go ahead and compute them. The angle should be nice in your problem as well, so that it relies on knowing facts about the unit circle to compute these, and the expressions are clean. Right. So converting them and then putting it all together, you have the coordinate in rectangular. Next one. So suppose you're given a coordinate, a point in rectangular coordinates. Find the way of naming it in cylindrical coordinates. So we use the formulas r is equal to r squared is equal to x squared plus y squared, and theta is equal to y over x. So you end up solving for r. So after plugging in, you take the square root. You get 3 radical 2. And then for this, after you plug in y over x, you would take the inverse tangent, and you'd get minus pi over 4. And so this is where I don't stick with that convention of making it lie between 0 and 2 pi. I'm totally happy with calling this, naming this point with theta being minus pi over 4. That, to me, is quite reasonable. Although, if you wanted to, you could enforce that it's between 0 and 2 pi, in which case, let's see. So we're talking about the angle here. So this is the angle. So if instead of being minus pi over 4, this would be 7 pi over 4 would be another way of naming that angle. 1357, yeah. Okay, now one thing to remark about this. So when you take inverse trig functions, you need to be a little bit careful. And so I concocted a example that shows the issue that can arise. So if instead of all I do is I change which quadrant or octant, if we think about the three-dimensional case. But if we project down, we're thinking about the quadrant that this point lives in. So instead of being over here, I use minus 337. So you end up being over here on the xy plane, this point, right? And so the angle, as you can see, it should be 3 pi over 4. But if you blindly use the formula, you do y over x and you take inverse tangent of it, you're actually gonna get the same. Oh, there should be a minus there, shouldn't there? Yes, there should be a negative here. So yeah, if you blindly apply the formula and you take inverse tangent of minus 1, you would get negative pi over 4, agreeing with what we did above. But as you can see, that angle is not minus pi over 4 by any means. So instead, you actually need to correct for which quadrant this is supposed to be living in. So this is saying a 45-degree angle in some quadrant, and in particular, using your geometric intuition, you would know this is supposed to be in the second quadrant. So it'll be 3 pi over 4. Okay. Yeah, so that can arise if your point were actually living in the second or third quadrants. Inverse tangent will force the point to be in the first and fourth quadrants, so you will need to be wary of that when you solve these kinds of things. Next problem, we're given a surface, the equation of a surface in rectangular coordinates, and we want to convert the equation over to being in cylindrical coordinates. So again, this is about applying the conversion formulas. So between cylindrical and Cartesian, we would use these, and sometimes you might need to use it's not certain which side of them you're using, so it's good to like see them all in one collection. In this case, what we do is we can actually just use the formulas that were on the left column. So y we know is equal to r sine theta when we try to convert over. And so we would get r sine theta is equal to 2. And then by dividing sine, I end up getting the reciprocal function, which is the reciprocal of sine is cosecant. So r is equal to 2 cosecant theta is how we could express this plane in cylindrical coordinates. Okay. We want to do the same thing here. I think it's actually in the same order as well. Rectangular to cylindrical. Yeah. So this time we're given, so if you can visualize this, notice that there's no z, in which case this looks like a circle. In fact, let's maybe just discuss how you can visualize this. So by completing the square, we'd get x squared plus y, let's see, so that is 16, divided by 2, we get 8. Divide by 2, we get 8. We would square it to get 64. X squared minus 16x plus 64 is equal to 0. We would get y minus 8 quantity squared, oh, not 0, equals 64. Equals 64, x squared. So we get this. So you can see that, and that's equal to 8 squared. So you can see that if we intersected this surface with the xy plane, or project it onto the xy plane, we get a circle. We get a circle centered at 0, 8 of radius 8. But, and z is allowed to roam freely, which means that from this circle, we end up extruding it in the. Just gonna do a quick sketch of this in. So in the xy plane, it looks like this. And we extrude it in the z direction so that it goes infinitely. So this is a cylinder, right? A cylinder whose base is a circle. So that's what this region looks like if you were to visualize it or plot it. Now to discuss converting this. So the convenient thing to notice about this is in this expression you have x squared plus y squared. And that whole quantity is equal to r squared if you look at the conversion formula. So let's scroll back up to that. So we end up using this side. And then I think for the other one, I might use the other side. I don't know. So yeah, minus 16x, right? So x I know is equal to r cosine theta. So I've ended up using formulas from both sides, right? So minus 16r cosine theta is equal to 0. So we end up with this formula. But then I decided to clean it up a little bit because I am actually able to do so in this case. So notice that you can factor an r out, which gives you this. And then this statement is saying that either r is equal to 0 or you have that r minus 16 cosine theta is equal to 0, right? Because one of these factors must equal 0 for this equation to hold. R equaling 0 is actually just going to be, well, it'll be a line, and it ends up being captured in this portion. So I'm able to just cancel that part of the equality away. And we are just left with r minus 16 cosine theta is equal to 0, which you then solve, and you get r is equal to 16 cosine theta. So just like if you worked with polar coordinate system, converting this over, you get the same thing. So this ends up describing a circle positioned on the y-axis. Okay. And then the next example, we have the equation of a surface in spherical coordinates, and we want to find the equation in rectangular coordinates and identify and graph the surface. So I didn't bother to graph it, I just expressed it in words. So we have the equation rho is equal to 2 cosine phi. Now, if you stare at the formulas you're given, cosine phi, right? This is, I think, the closest that you can get. to have a cosine phi, and then notice that in order to get the rho, you would multiply both sides by rho. So what ends up happening is that both sides end up being by multiplying both sides by rho, you end up having both sides be things that are easily convertible to to the Cartesian coordinate system, right? You end up using this formula and this formula by multiplying both sides by rho. So that's what happens in these sets of lines. So rho squared is 2 rho cosine phi. Cosine phi is equal to z, so you get 2z on the right-hand side. On the left-hand side, you get x squared plus y squared plus z squared. Subtracting 2z over and then completing the square, adding 1 to both sides so that you can complete the square. You end up with this equation, and then you can easily identify that this is a sphere centered at 0, 0, 1 with radius 1. And of course, you could sketch this pretty easily if you wanted to. And that's all I've got for this video.